Hello everybody, getting ready to do section 1 of SAT Math Level 2 preparation. And for our first part 1 here for section 1 functions, definitions, combining functions, piecewise functions, inverses, odd and even functions. You got 18 points for your notebook guide, and then 8 points will go onto your classwork sheet. Have that out in front of you. Name, date, period in my class, due date for onliners, homeschoolers. And we go into page 1 here. We'll go into your notebook, part 2 of the review of major topics. So we're going to review major topics now to get you ready for your level 2 test. This part reviews the mathematical concepts and techniques for the topics covered in level 2 mathematics subject test. A sound understanding of these concepts certainly will improve your score. The techniques discussed may help you save time solving some of the problems without a calculator at all. Calculators are fast, but for problems requiring computational power, techniques are described that will help you use your calculator in the most efficient manner. Your classroom experience will guide your decisions about how best to use a graphing calculator. If you have been through a secondary mathematics program that attached equal importance to graphical, tabular, and algebraic presentations, then you probably will rely on your graphing calculator as your primary tool to help you find solutions. However, if you went through a more traditional mathematics program where algebra and algebraic techniques were stressed, it may be more natural for you to use a graphing calculator only after considering other approaches. So with that said, let's go into definitions now. Function is a process that changes a set of input numbers into a set of output numbers. A particular input number will always produce the same output number. However, a particular output number could be the result of applying the function to different input numbers. Functions are usually specified by equations such as y equals radical 2x minus 1. In this specific equation, x represents an input number while y represents the unique corresponding output number. Functions can also have names in the example. So we could name the function f. Then the process could be described as f of x equals radical 2x minus 1, whereby f takes the input number x, multiplies it by 2, subtracts 1, and then takes the square root to produce the output of y equals f of x. Taken as a group, the input numbers are called the domain of the function, while the output numbers are called the range. Unless otherwise specified, the domain of a function is all real numbers, for which the equation produces outputs that are real numbers. Example above, the domain is a set of x is greater than or equal to 1 over 2, since 2x minus 1 cannot be negative if y is to be a real number. In this case, the range is a set of all non-negative numbers. The domain of a function can also be established as part of the definition of a function. For example, even though the domain of the example function f is x greater than or equal to 1 over 2, one could specify the domain as x greater than 5. Unless the domain is explicitly stated, the domain is assumed to be all real values that produce real numbers as outputs. So deal with real numbers within the level 2 SAT. A function with a small finite domain can be described by a set of ordered pairs instead of an equation. The first number in the pair is from the domain, and the second is the corresponding range value. Consider, for example, a function f consisting of the pairs 0, 2, 1, 1, 2, 3, and 3, 8. In this example, the process is not systematic. It simply changes 0 to 2, f of 0 equals 2. 1 to f of 1 equals 1. 2 to 3, f of 2 equals 3. And then f of 3 equals 8. The domain of this function consists of 0, 1, 2, and 3, while the range consists of 2, 1, and 3, and 8. Functions like this are typically used to illustrate certain properties of functions and are discussed later. A function is actually a special type of relation. A relation describes the association between two variables. An equation such as x squared plus y squared equals 4 is one way of defining a relation. All ordered pairs, x, y, that satisfy the equation are in the relation. In this case, these pairs from the circle of radius 2 centered at the origin. So this is an equation of a circle. Note that in a relation, unlike a function, a particular input number might be paired with more than one output number. Circles are examples of relations that are not functions because some x values, 0 in the example, have two y values associated with it, 2 and negative 2, which violates the uniqueness of the output for a given input. Other than circles, relations that are not include ellipses and have two y values associated with it, 2 and negative 2, which violates the uniqueness of the output for a given input. Other than circles, relations that are not functions include ellipses, hyperbolas, and parabolas that open right or left instead of up or down. In other words, the conic sections, which will be discussed in chapter 13 or section 13. Like functions, relations can also be defined using specific ordered pairs. The set of r equals 1, 1, 1, 2, 2, 1, 2, 2 is an example of a relation that is not a function because the x value 1 has two y values, 1, 1, 1, and 1, 2, associated with it, 1 and 2. So technically a function. A graph is a graph of a function if it passes the vertical line test. Since a vertical line represents an x value, a graph passes this test if no vertical line intersects a graph on more than one point. Given two functions f and g, 6 new functions can be defined as a sum function, difference function, a product function. So here's an example here of a sum function, f plus g of x. This is how you would add them, combine them together. And then difference functions, f minus g of x, f of x minus g of x, and f times g of x equals f of x times g of x. This would be a product function here. And then we go into a quotient function, which would be a f over g of x, and this is how it would present itself here, f of x over g of x. Of course, g of x can equal 0, and then a composite of functions, f of g of x would be f of g of x, and then g of f of x would be g of f of x. These are composites here. So, if f of x equals 3x minus 2 and g of x equals x squared minus 4, write an expression for each of the following functions. So for a here, we have f plus g of x. So we could write that like that. And then if we use these up here, this is our f of x, this is our g of x, then we need to add these two values, these two functions together, and this is what we end up with there. For a sum of these two, a. And then b here would be the difference of two functions, f minus g of x, and the way that that would present itself, f of x minus g of x. And then once we do that, we have 3x minus 2 minus x squared minus 4. And then when we combine similar values, we end up with this expression here. And then for C, f times g of x, so we have a product function here, a product of functions, f of x times g of x, and we multiply these together like this, we end up with this expression here, 3x cubed minus 2x squared minus 12x plus 8. And then D here, we have f over g of x, which looks like a quotient function. So this would be f of x over g of x, so 3x minus 2 over x squared minus 4. And x cannot equal plus or minus 2. So that would be the way this would present itself here. And then E would be f of g of x. So to do that, f of g of x would be f of g of x, so it would be 3 here. So 3 would be g of x minus 2. So we substitute g of x here for x is what we do that. So the 3 times g of x, we put g of x here for x. So we have 3 times x squared minus 4 minus 2. And then when we combine similar values here, we end up with 3x squared minus 14. 3 times negative 4 minus 2 would be negative 14. And then we have f of g, f here will be g of f of x. So when we do that, we have g of f of x would be f of x squared minus 4 would be that. So g would be x squared. So we plug in f of x for our x here and g of x, and then we square it. And then when we do that, we have 3x minus 2 squared minus 4. And then this would yield a 9x squared. 9x squared here. And then minus 12x here. So when we square this, we have 9x squared minus 12x. When we get that from this here, then when we square that, that would be what would that be? It would be 3x squared, and then we get a negative 12x, and then we square negative 2, that would be positive 4. Combine those two together, we get 0. So we just end up with 9x squared minus 12x when we square this. The inverse of a function f, denoted by f to the negative 1 power, is a relation that has a property that the inverse of f times f of x equals f multiplied by the inverse of f of x will equal x for all x in the domain of f. So that's a fancy way of saying that when you multiply the inverse of a function by the inverse, when you multiply a function by its inverse, we'll end up with x, basically is what it means. When you stick in the inverse of a function into the function, you'll end up with x. And then this one here, when you have f and then you stick the inverse into f of x, so you'll end up with x for all x in the domain of f. The next two examples show how to find the inverse of a function and verify that it is the inverse. To do that, we have given 3x plus 2 is f of x, and then find the inverse of f of x. So to do that, first write in place of f of x, write y in place of f of x, and interchange x and y. Then solve for y and call the result g of x. So to do that, we have x equals 3y plus 2, so we're going to put in y for x. So y will equal g of x equals x minus 2 over 3. So when we solve for y here, which becomes g of x, y will equal x minus 2 over 3. G is the candidate for the inverse of f. And then for h here we have 3x plus 2. If g of x equals x minus 2 over 3, is that the inverse of f? So we need to prove that it is. So to do that, we're going to go g of f of x. So we have g here. This is g, then g of f of x. So we plug in here for x, we plug in 3x plus 2. So we have 3x plus 2 minus 2 over 3. And then these cancel out. Then this will cancel out. So we end up with x. So that proves that it is the inverse. So therefore, f of g of x equals f of g of x equals 3 times x minus 2 over 3 plus 2 will equal x, and it does. Therefore, g is the inverse of f. G equals the inverse of f. The inverse of a function is not necessarily a function. So, okay, that's good to know. So f of x equals x squared. Find the inverse of f. So to find that, write y in place of f of x. So we write y here, y equals, and interchange x and y. So we have y equals x squared. Then solve for y and call the result g of x. So in this case here, x will equal y squared. So y equals g of x, which equals plus or minus radical x. So since a given input x produces two output values, x and negative, a radical x and a negative of radical x, g is not a function. So okay, g is not a function, but it's still the inverse. Find the inverse of f. So we have 1, 2, 2, 3, and 3, 2. This is f, so we need to find the inverse of this situation there. So to find that, we have to interchange x and y to get the inverse of f. So here's 2, 1, 3, 2. So we're gonna inverse our ordered pairs here. Since the input 2 produces two outputs, so the input 2 produces outputs here. 2 is 1, and then 2 equals 3 here. It produces two different outputs. 1 and 3, the inverse of f is not a function. Okay, cool. So that is section 1 of your SAT Math Level 2 Prep. Animated PowerPoint Math Video at AOL.com is my email. Thank you very much for materials or questions. Thank you.